Good afternoon, everyone. The topic which I'm going to deal with you is geometrical isomerism. So, this concept, geometrical isomerism, you would have studied even at school level. The basic concepts of geometrical isomerism you would have studied, and the detailed discussion on geometrical isomerism today we'll see. So how to define the geometrical isomerism? So the definition we give for geometrical isomerism here is that if two molecules, if they have the same molecular formula, same structural formula, but they differ only in the spatial arrangement of atoms and groups about the doubly bonded carbon atoms. For example, see here. So this is a carbon, this is a carbon double bonds. So these two are similar groups. Here the similar groups are lying on the same side about the carbon double bond, whereas here the similar groups are trans to each other about the carbon double bonds. So this kind of isomerism is called as geometrical isomerism, and these two are called as geometrical isomers. So example is fumaric acid. This is a cis form of fumaric acid, and this is a trans form of cis isomer. This is a trans isomer. This is called as maleic acid. This is called as fumaric acid. Okay, here when the two groups lying on the same side of the molecule, both the carbon double bond, is called as a cis isomer. When the similar groups, when they lie on the opposite sides of the both the carbon double bond, they are called as trans isomers. So in the case of geometrical isomerism, the isomers exist as cis and trans forms. And then some of the properties of this geometrical isomers are they do not have any mirror image relationship, and free rotation is not expected here, since there is a double bond exists between the two carbons. We do not expect any free rotation here. So it is very difficult for the molecule to to undergo rotation. So even if it undergoes a rotation, the rotation is called as restricted rotation. So no free rotation is expected here. Then it exists as a cis and trans forms. One example I gave you is maleic acid, fumaric acid. The second example is cis to butene and then trans to butane. This is cis to butane. Here also the similar groups are placed lying close to each other about the carbon double bond, whereas here the similar groups are placed oppositely. That is, they are trans to each other about the carbon double bond. So this is called as a trans butene. This is called as cis butene. And then in the structure 1, that is in this structure or in this structure, here the two methyl groups are lying on the same side of the molecule. See here, the two methyl groups are lying on the same side of the molecule. Here the two methyl groups are lying opposite, they are placed trans to each other. So this is structure 1 and this is structure 2. And when this kind of arrangement is seen in that molecule is called as, it exists as cis form, and when this kind of arrangement is seen, that molecule exists as in a trans form. Then coming to the stability of this cis to butene and trans to butene, or cis isomers and trans isomers. So when we compare the stability of these two isomers, trans isomers are found to be more stable when compared to cis isomers. Okay, so the reason we give for this one is, see here since both the bulky groups are lying close to each other about the carbon-carbon double bond, here it undergoes, it is found to be a highly reactive molecule. Whereas in the case of trans isomers, since the bulky groups are placed diagonally, they are placed opposite to each other about the carbon-carbon double bond, this molecule is found to be a more stable one when compared to cis isomer. So cis isomers are less stable, whereas trans isomers are more stable. So this is the stability. There is a when you compare the stability of these cis isomer and trans isomers. Trans isomers are highly stable when compared to cis isomers. The reason behind here is trans isomers. In the case of trans isomer, there won't be any steric hindrance, since the bulkier groups are placed diagonally opposite to each other, whereas in the cis form they are placed similar to each other. The bulkier groups are lying close to each other, so it is found to be highly reactive. So there may be some intramolecular reaction occurs here. So it is found to be a highly reactive one. The cis isomers are highly reactive, whereas trans isomers are not highly reactive. They are found to be highly stable one. Stability wise, trans isomers are highly stable. Then coming to this determination of the configuration of geometrical isomers, that is how are we going to determine the configuration of some geometrical isomers, for example, cis form and trans form. How are we going to differentiate the cis form and trans form? So we have so many methods are available, physical methods as well as chemical methods. Today we'll discuss only the chemical method of determining the configurations of geometrical isomers. So the chemical method we use here is a method of cyclization. So the principle behind the method of cyclization is the first point we have to note here is the intramolecular reactions occurs in the case of cis isomer. That means in the case of cis isomer, since the similar groups are lying close to each other, there may be the possibility of intramolecular reactions occurs more likely. That means the closer together the reacting groups are in the molecule. So whereas in the case of trans isomer, it is not so. So this principle is applied for the reactions in which a new ring is formed, and this principle is not applicable for the other elimination reactions and for molecular rearrangements. We'll see some examples. How are you going to differentiate the cis form from the trans form? See, among the two acids, maleic acid and fumaric acids, maleic acid, see here, this maleic acid, this is one is fumaric acid, this is maleic acid. Among these two acids, maleic acid, which is a cis isomer, since two bulkier groups are placed, they are lying close to each other about the carbon-carbon double bond. So some intramolecular reactions would have occurred here. So there may be some elimination of one molecule of water, giving rise to the maleic anhydride. So there will be an easily that maleic anhydride is formed from the cis isomer. Whereas in the case of trans isomer, since they are highly stable, they are found to be highly stable. Since the two bulkier groups, they are also placed diagonally opposite to each other, there is no possibility of the intramolecular reactions to occur here. So this is another reason. So the one which easily forms the cyclic anhydride is the cis isomer. The other one which do not form the anhydride is called as the trans isomer. So this is how we use to differentiate. We differentiate that malic acid from fumaric acid, that is from cis isomer from trans isomer. So this is one of the best method. There is method of cyclization is one of the best method to differentiate a cis isomer from the trans isomer. There's another example here we find here is a citroconic acid and isogonic acid. The citroconic acid here this is a cis isomer and this is going to be a trans isomer. Since both the bulky groups are placed, they are lying close to each other, there may be the possibility of the intramolecular reactions here. Whereas here, in the case of mesoconic acid, since bulky groups are placed diagonally opposite to each other, there is no possibility of the intramolecular reactions to occur here. So this one is a cis isomer. The one which easily forms the cyclic anhydride is the cis isomer. The one which hesitates or which do not form the cyclic anhydride easily, that is called as a that is called as a trans isomer. So citroconic acid is a cis isomer and the mesoconic acid is a trans isomer. So there is another example also we have. That is Comernic acid and then Comernic acid and then Coumaric acid. So Comernic acid is a cis isomer, whereas Coumaric acid is a trans isomer. Comernic acid is here the COOH group and the OH groups are closer to each other. There is a possibility of the formation of the intramolecular reactions to occur. Whereas here there is no possibility of the formation of the intramolecular reaction since the OH groups and COOH groups are placed, they are away from each other and they are placed diagonally opposite to each other here. So the one which readily forms the anhydride, this coumarin, this is an anhydride of this acid. This one, the one which easily forms the anhydride is the cis isomer. The one which do not form the anhydride is the trans isomer. So this is how we are able to differentiate the cis isomer from the trans isomer. So hope you have followed the basic concepts of geometrical isomerism and then stability of the cis form and the trans forms, and then how to differentiate the cis forms and trans forms through the method of cyclizations. So all these things you would have learned, you have learned today. So thank you very much for listening to this lecture. Thank you.